Hi guys, today's class I would like to discuss continuous charge distribution. So concept number 1.13, continuous charge distribution. Till now we discussed what are the charge effects if the charge is a single charge or a dipole. Now we are extending the concept. What happens if you take a charged object, maybe one dimensional object or two dimensional or three dimensional object, and because of that charged object at a certain point, what could be the electric field due to this charged object? So to find out the electric field or force due to this charged object, we need to know what's the total charge on the object. So in this concept, we would like to find out how we would find electric field or force due to continuous charge distributions, either one dimensional or two dimensional or three dimensional. So in this concept, we will discuss first linear charge distribution. Under the first case, I would like to discuss linear or line charge distribution. Line charge distribution. Suppose, imagine a case. So we are having a very thin charged object. So this is having a charge of positive on it. So since it's a very thin, so we can take it's only one dimensional object. Now our task is to find a force due to this line charge distribution or due to this object. Suppose if I take at a point P at here, so for imaginations, if I bring a test charge Q naught right at there, I would like to find what is the electric force due to this object at here. The distance between them, let it be R. Now, earlier case, we understand how to deal with a single point charge. We directly apply the Coulomb forces, so we can figure it out. But at here, if we can take this as a bigger object, suppose if we assume that this is an infinite line charge or infinitely long thin wire. So because of this all charges, force will be exerted at the point P. To find out that, here we need to define a new definition. So for that, first I would like to take a small portion in this object. Suppose if I take this is a small portion. So this portion is from here to here. I can call an elemental length dl. Suppose this object having as a total length we can take as L and total charge as Q. So if the total length having charge Q, we need to figure it out what is the charge present in this small elemental length. For that, I can take an assumption. So the dq is the amount of the charge which is present in this small elemental length. Now if you write the ratio, so it means the dq by dl, that we can define as, we can represent as a lambda, and this ratio we call it as line charge density. line charge density. So here the new term for us, it is charge density. Charge density. I hope you know the what is the realistic meaning of density. Whenever we talk about density, at once it comes to our mind, it is the mass by volume. If it is a three-dimensional object. But here precisely we are calling charge density. So charge per unit volume if we take three-dimensional object. But here our object is as infinitely thin object. So that's why we call it as line charge density. So we are representing that as lambda with lambda equal to dq by dl, the ratio of charge per unit length. So the units of lambda, charge units are coulomb and length units are meter. We can write it as coulomb meter inverse. So by using this definition, linear charge density, I can write from the above expressions. So dq equal to lambda times dl. It means right now I came to know in this elemental length how much charge is present. So I came to know that in that elemental length how much charge is present, lambda times dl. Now here we are ready to apply the Coulomb's law. So to find out the force due to linear charge distribution F suffix L. So here the Coulomb force, I can write that. First I would like to write this is a small amount of the force dFL, which is equal to 1 over 4 pi epsilon naught. So dq is the charge on the elemental length times the q naught, what is the test charge what you have taken, and the distance square r square, and the direction of the force, it is along the unit vector direction r roof. Now substitute the dq value at here. So now you can get the small amount of the force due to the small elemental length dl. You can get 1 over 4 pi epsilon naught dq value lambda times dl times q naught by r square, and the direction r roof. Now if this is the small elemental length, force due to small elemental length, but we need to find out what is the total force. Total force, that is F due to line charge distribution. To get the total force, we need to integral for the total length, integral dFL. So here the integral terms, non-integral terms, first I will pull it out. What are the non-integral terms? 1 over 4 pi epsilon naught, lambda is constant and q naught is constant. So we need to integral dl by r square for the total length. So this is a line integral, and the direction r roof. So we can write finally the above expression as a fancy manner. F suffix L, the force due to the line charge distribution, lambda times q naught upon 4 pi epsilon naught integral. It's a line integral since it is a linear charged object, dl by r square, and this force is along the r vector direction. So this expression helps us to find out what is the force at that point due to because of the whole object. Once if you find the force, it is to find the electric field also. Now electric field at point P equal to electric field formula, electric field equal to force per due to the line charge to test charge. We need to divide with the test charge. So in the above expressions, if you divide the terms, so lambda q naught by 4 pi epsilon naught line integral dl by r square times r roof by q naught. So the test charge gets cancels. Now we can write the electric field due to line charge distribution. Expression for electric field. The net electric field due to this line charge distribution, lambda by 4 pi epsilon naught integral, it's a line integral. So dl by r square times r roof. So this is the expression to find out what is the electric field due to this line charge distribution at a given point. So here we introduced a new definition. That definition is known as line charge density. That we define as charge per unit length. We are representing that lambda equal to dq by dl. Now let's see the another case. So that is surface charge distribution. Surface charge distribution. What does it mean? Suppose I have a two-dimensional object. So let this two-dimensional object, two-dimensional charged object. So now in this one, if I take it is positive charge, it means it is positively charged object. Two dimensions, positively charged object. So everywhere positive charges existed. Now our task is to find an electric field at a given point P because of this charged object. So we need to figure it out what is the electric field at point P, which is at a distance r because of this charge distribution. Now how we would proceed? For that, let us consider a small surface. Let us consider a small surface in that two-dimensional object. So this is my surface. So I wish I would like to highlight to know that is surface. Now here our method is, first we will find what is the force due to this small surface at that point P. Later we will do the integration for the whole surface. So that is what we did in the earlier case. So to find out the force due to the small surface ds, I need to find what is the amount of the charge contains on that surface. Now here the small surface equal to ds, which contains amount of the charge dq. Now with this help we are defining another definition called surface charge density. Surface charge density. It's a charge density. So we are representing that as sigma equal to dq upon ds. Charge per unit surface. Since it's a two-dimensional object, so we need to take its surface. So the ratio of the charge to a unit surface we defined as charge per unit surface. From that above expression, and if you write its SI unit, charge units are coulomb and surface units are meter square, we can write coulomb per meter square. So from this expression, I would like to figure it out what is the amount of the charge present on the small surface which I have chosen it here. So the amount of the charge present dq equal to sigma times ds. Yeah. If I know the amount of the charge which is present in the ds, and it is easy to me to find out what is the electric field or the force at a given point. To find out the force at a given point, I have taken a test charge Q naught at the point P. Now you can apply the Coulomb force. By Coulomb force, we can write that the electrostatic force due to the surface, the small force due to the surface equal to, it's 1 over 4 pi epsilon naught. Charge on the surface equal to dq, and what is the charge on that point P? It's a q naught upon distance is r square and the direction is r cap. Now in the place of dq, substitute the value of the dq. It's 1 over 4 pi epsilon naught. Dq value at here I will get sigma times ds times q naught upon r square times r cap. Now to find out the total force due to the surface at point P, to find out the total force, what shall we do? We need to do integration. The total force due to the surface equal to integral, its surface integral df. So we can pull it out, the constants of integration, 1 over 4 pi epsilon naught times integral, it's a surface integral, sigma times q naught by r square dot ds times r cap. So that is the total expression for the total force. So if you can write that in order, the total force due to the surface 1 over 4 pi epsilon naught times, I would like to pull sigma and q naught outside since they both are the constants, sigma q naught times surface integral 1 over r square times ds, finally r cap. So r cap is unit vector. So this is the net force due to the surface at that given point. Once we find out the force, we can easily figure out what is the net electric field at that point. Therefore the net electric field at point P, so we can write electric field due to the surface equal to force per unit charge. We have to divide with unit charge. So in the above expression, 1 over 4 pi epsilon naught sigma times q naught times surface integral 1 over r square times ds times r cap upon q naught. So q naught gets cancels. So the electric field expression due to the surface, electric field Es bar equal to 1 over 4 pi epsilon naught times sigma surface integral 1 over r square dot ds times r cap. So by seeing this expression, don't be frightened. So it's a very easy. So this is the electric field expression to find out what is the electric field due to this surface at the given point. So because of this charged surface, we define a definition at here that's known as surface charge density. According to this definition, charge density, surface charge density sigma equal to charge per unit surface. Let's see the third case, case 3, that is volume charge distribution. Volume charge distribution. It means in this case we need to take an object which is having a volume. So consider this is an object having volume. So in this object, suppose if you take it's a charged object, it means charge is present in this volume object. Okay. Now as usual I would like to find an electric field at a given point. So this is the point P, due to because this volume object, charged volume object. So for that, if I take, so the unit vector distance, so this is the at a distance, the point P is at a distance of r, so the distance is r. Now to find out the what is the electric field due to this charged volume object, first we need to find what is the amount of the charge present on that object. For that, I would like to assume a small elemental volume. So it's should be 3 dimension, but in the figure I can show it as 1 dimensions. So this small element is having volume dV, elemental volume dV. So if the total charge, if the total volume, if you can take as V, and total charge on the object equal to Q. If you take like that, so if volume equal to dV, so what is the amount of the charge present on it? We can take that as dQ. Now here we define another definition, the ratio of dQ by dV. The ratio of dQ by dV we represent as rho, so it's pronounced as rho, RHO. So this we define as volume charge density. So that we can write it as volume charge density. Means charge per unit volume. Now from this definition, I came to know that what is the amount of the charge present in this small volume which I have chosen. So the amount of charge present in the given volume dQ equal to it's rho times dV. If I know what is the amount of charge present on it, then it's easy to me find out what is Coulomb force. After that, what is electric field. So for that, at the point P, I would like to bring a test charge Q naught. So Q naught is my test charge at the point P. Now we will write the force, small force due to volume object at a point P equal to 1 over 4 pi epsilon naught small charge on the surface dQ times test charge and Q naught by r square and its direction along r roof. To find the total force, so we need to do integration, that is f suffix v integral dfv. So this is we can call volume integral. So we can do the integration. Suppose if you can take 1 over 4 pi epsilon out of integration, so integral dq times q naught upon r square times r roof. So substitute the value of dq at here. So in the place of the dq, so I can write, so the force equal to 1 over 4 pi epsilon naught. So integral rho dv by r square times q naught in the numerator times r roof. R roof will gives the unit vector direction. Now if you can write that constants outside, we can represent that very easily. So the total force Fv equal to 1 over 4 pi epsilon naught, it is Coulomb's constant, and here rho also a constant and q naught is also constant. We can pull it out of integration times 1 over r square times dv, that is the volume integral everywhere, times r roof. So this is the electric force or Coulomb force expression at that given point P. So if you know Coulomb force, we can find then electric field at point P due to volume object, volume charged object. So I can define electric field due to volume charged object equal to force per test charge. So we need to divide the above expression with the test charge. If you can divide with the test charge, so the test charge terms will be cancels out. So the leftover term I am writing directly. So 1 over 4 pi epsilon naught rho times, so volume integral of 1 over r square times dv. Finally, you will write the unit vector direction r roof. So this is the electric field expression due to the if any volume object. So this is the way to find out the electric field. But later section we will discuss a theorem, Gauss theorem. So that makes us our problems very easy. So but you need to get the knowledge of three definitions. First one, volume charge density. So volume charge density can define as charge per unit volume. So that we define as volume charge density, charge per unit volume. At the same time, I would like to define one more definition, that's called as surface charge density. It means charge per unit surface. So dq by ds, that we are representing with the sigma. Finally, linear charge density, charge per unit length. So the charge per unit length we define as linear charge density.